When we left off, we were near the top of page 46 on the handout I gave you. And the current topic is interference from a thin film. If you have, for example, well, one place you see it is walking across a parking lot on a rainy day. So you've got puddles. And some car recently went by and it was dripping gasoline or transmission fluid or motor oil or whatever. You get a little drop of oil floating on top of the water. So light comes down from above and some of it reflects off the top of the oil, but most of it goes on through. Some of it reflects off the top of the water, but most of it goes on through. But you now have two beams of light headed back toward your eye, one from the top of the oil slick and one from the bottom of it. And because the one that reflects off the bottom has to travel a little farther to get to your eye, there's the path difference that gives you interference effects. But as I was saying the other day, there are complications, a couple of them. What kind of interference you get depends on how the difference between the two paths compares to the wavelength of the light. But the wavelength of the light changes when it crosses from one material into another. In the example I just gave with the oil floating on the puddle, it's the wavelength in the oil that you need to consider. And I'm going to close that door. The wavelength in the oil compared to wavelength in the air is shortened by a factor of n, the index of refraction, which is how n gets into these equations that are written here for thin film interference. The other complicating effect is that sometimes when a wave reflects, it gets flipped upside down, but other times it doesn't. And this depends on whether the wave is reflecting off of a higher index of refraction or a lower index of refraction. This is the reason why there are two sets of formulas. Maybe I'll switch this over for a moment. This is the formula sheet that you get to look at when there's a test or something. And at the very top of the 5th page on the formula sheet, I put down, that there's a by a 180-degree phase shift. That's just another way of saying the wave gets flipped upside down. It gets flipped when it bounces off of a larger index of refraction, such as light in air bouncing off a glass. It does not if you have something like light in glass bouncing off of air. Anyway, notice that there are two sets of equations to refer to when you're working with thin film interference. The ones on the left here say that the n it refers to is the n of the thin film, okay? When it says n higher or lower than what's on either side of it, that means, well, for example, for part of the lab, the thin film is going to be a very thin gap. The thin film is made out of air, a thin gap between two pieces of glass. And that would be a case where n is lower than what's on either side of it, okay? Air is around 1.0, glass around 1.5. So you would use these two equations to tell you where destructive and constructive interference is in that case. On the other hand, an n in between what's on either side, that would be like the non-reflective lenses that I was talking about the other day, where you have a piece of glass whose index might be around 1.5, coated with some other material whose index of refraction might be around 1.3-ish. And then beyond that, there's air. So you got air on one side, glass on the other. The coating has an index of refraction between what's on either side of it. And you see the equations are switched. The one that gives you constructive interference in the one case is the same equation that gives you destructive interference in the other case. That's because over here, well, maybe over here, if n is in between what's on either side of it, over here on the right, then depending on which direction the light is traveling, both rays either reflect off of a higher n or a lower n. They both experience the same phase shift. So if you've got, for example, a path that's T is the thickness of the film, and if that's practically zero, then I guess I should be pointing at this one. If T is practically zero, then you get constructive interference, which is what you would expect if you didn't know anything about these, flipping upside down. On the other hand, in this case over here, one of the waves gets flipped over, but the other one doesn't. And that switches things around. When the path difference is practically zero, m times lambda is practically zero because it's such a thin film, then you get destructive interference instead of constructive. So anyhow, that's what's going on. Continue on down the page. I was kind of in the middle of talking about that when we ran out of time last time. If you're talking about a puddle in a parking lot, you don't have monochromatic light in a parking lot. You've got sunlight, which is a fairly even mixture of all the different colors in the visible part of the spectrum. And so at a given spot on the puddle, some colors will be strongly reflected, other colors will be strongly transmitted. It's all a matter of, going back to the formula sheet here, it's all a matter of how the wavelength compares to the thickness of the oil, okay? The wavelength for some colors will give you constructive interference, which means it'll be strongly reflected. The wavelength for other colors will match up with the condition for destructive interference. Those colors will go on through almost entirely instead of being reflected back toward you. But the oil over here might be a little thicker than it is over there. So maybe over here, green is strongly reflected, whereas over there, red is strongly reflected. And that's why you get the colors. And these are, if it's a nice fresh one, I mean, I've been walking across a parking lot on a wet day and seen these things, and it looks kind of like a bullseye. You've got these concentric rings of different colors, and that's because it's a nice fresh drop of oil, and it's still thicker in the center and thinner out on the edges, and it hasn't been driven through a few times yet and made more complicated. And so as you go from the center toward the edges, and the oil gets thinner and thinner and thinner, it's rings of different colors that are strongly reflected. It's the same sort of thing with the colors you see in soap bubbles. The bubble is not the same thickness everywhere. And so in some places it strongly reflects this color, but in other places it strongly reflects that color, and so on. So that's what this little paragraph here says. So now here's a problem. This would be a non-reflective lens, and it's asking you how thick the coating should be. If this is the wavelength you want to have it be completely non-reflective for. the first step is to pick the right equation. You've got stuff all over the top quarter of the formula sheet there on that page. The first thing to do is to narrow it down. In this question here, the thin film has a refractive index of 1.38. The air that's on one side of it is 1.0. The glass on the other side of it's 1.55. 1.38 is between 1.0 and 1.55. So that means we're over on the right here where it says N between what's on either side. The other thing you have to understand is that non-reflective lenses work by destructive interference. The ray reflected off the top of the coating and the ray reflected off the bottom of the coating destroy each other, and that's why there's no reflection. All the light has to go on through and be transmitted. So in that little group on the right, you go for the equation for destructive interference. N of the coating is between the ends on either side of it. Destructive interference occurs where 2NT equals M plus 1/2 times the wavelength in a vacuum, to be precise. Fill in numbers. N is the refractive index of the coating. Every now and then somebody wants to stick in the number for the glass, but it's the thin film's interference, 1.38. T for thickness is what the question asks for. What to use for M? Well, M is a whole number, 0 or 1 or 2. And any of those numbers ought to make the lens non-reflective. But what's done in practice is they just go for the minimum. You know, why make the coating 3 times as thick? Let's just go with M equals 0. And the 550 nanometers is the wavelength that the light would have in a vacuum. So now we've got it down to where it's just math. Divide for all practical purposes, you might as well call it 100 nanometers. And let's see what the bottom of the page looks like. Single slit interference. This might be a little bit surprising at first that you could get interference from a single slit, since interference effects come from a path difference. This ray travels a different distance than that ray, and that's what gets them in phase or out of phase and causes an interference pattern. So how do you get a path difference when there's only one slit? Well, when we were doing double slit interference, I was assuming that the slits were very narrow, okay? But let's consider a slit that's maybe wider, maybe like a whole 1/10 of a millimeter or something, well, not quite enormous like that. Then if you consider light rays headed for this point on the screen down here, Notice the bottom of the slit is a little closer to that point than the top of that, the top of the slit is. So this ray up here is a little longer than that ray down there, and the ones in between have in between lengths. And that's how you get your path difference that gives rise to interference effects. Let's start in the middle and work our way out. So if you consider the point on the screen that's directly across from the slit, okay? And again, as with the stuff I did earlier, this is not drawn to scale. So the screen would be many times, the distance of the screen would be many times the width of the slit typically. Right directly across, theta equals 0. All those rays are practically the same length. And so you get constructive interference. And so right in the middle of the pattern, there's a bright spot. So that's the first thing in the box there. Central maximum at theta equals 0. You start working your way to the side, either way, up or down the picture. You get far enough to the side, and the ray that goes through the very top of the opening will be half a wavelength longer than the ray that goes through the middle of it. So those two cancel. And the next ray down in the top half of, that came through the top half of the slit will also be half a wavelength longer than the next ray down in the light that went through the bottom half, and so on and so on. So you get far enough to one side, and the rays that went through the top half of the slit cancel the rays that go through the bottom half of the slit, and the screen will be dark there. And that would be the first of these minima, where a sine theta equals m times lambda. That would be m equals 1, the first one you get to. There is no m equals 0 in this case, unlike the equation for two slits. You get still further to the side, and the rays are even steeper there, so there's more of a difference between them. The rays in the topmost third of the slit cancel with the rays going through the middle third of the slit, which leaves the bottom third uncanceled. And so you have not as bright as the central maximum, but another bright spot there, where a sine theta would equal 1.5 lambda. Still further to the side, the rays that pass through the top quarter of the slit cancel with the rays going through the second quarter, and the third quarter cancels the fourth quarter, and you get your second minimum. Beyond that, the rays going through the top fifth of the slit cancel with the rays going through the second fifth, and the third fifth cancels the fourth fifth, leaving the last fifth uncanceled, and so on and so on. So as you work your way outward, the maxima become fainter and fainter. And unlike the double slit pattern, the central maximum does not fit the same equation as the other maxima. You have to state it separately. It seemed simple enough to set this up. This seemed like a good time to do a why should you take my word for it kind of thing. You guys might want to get out of your chairs where you can see a little better. Turn off the lights as you go by, would you? What I have done over here is I have set up a neon laser right there, and I just simply pointed it at a digital caliper. I have, that's a good angle. Yeah, right there, see? I've got just a tiny little gap, a little more than 1/10 of a millimeter between the jaws there. And the light hits the whiteboard over here. So if I hit it with the cord, I'll wreck the alignment and you won't have any pattern. people watching this are probably getting seasick because is that caught on something?
Yeah.
I was going to get him kind of a close-up. Thank you. So, yeah, it shows up pretty well. So you've got the central maximum there. Big wide blob of light. The side orders are smaller, unlike a double slit pattern where it would look just like a string of yellow. I got to go back to kindergarten and work on my colors. Red pearls, you know, that's just evenly spaced dots. With a single slit pattern, you've got that big central maximum and the fainter side orders. And so single slit interference. And now you've seen it. And I'll put the camera back down and stop jiggling everybody around. Oh, I guess we need the lights back. Got it? Thanks. Time to turn the page. One reason single slit interference is significant. I mean, another application is you could use that to measure the wavelength of light. My caliper would tell me, you know, you just read it off the digital display, it would tell me how wide the jaws are for measuring up the interference pattern. I could then calculate the wavelength of the light, basically measuring it with a digital caliper. But maybe more significant than that is what you just saw is what limits the resolution of any sort of an optical instrument. Telescope, for example. So you buy yourself a little telescope and you look at a star and it's kind of fuzzy. And what could you do to make it sharper? Well, a good example to have in mind is a binary star, okay, where you've got two stars that are very close together. The question is, how close can they be? And you can still tell that it's two stars and not one, okay? That's a much simpler picture to be looking at than Aunt Gertrude standing in front of the Washington Monument or something like that. Basically, you've only got two little point-like sources instead of a much more complicated picture, but it's the sharpness of the picture we're talking about. So we'll have that simple case in mind. Well, the first thing you can do to get a sharper picture is better optics. Don't buy your telescope from some discount store. Get one where the main mirror and the eyepieces and everything have been figured to a small fraction of a wavelength tolerance. That'll clear it up some. But a bigger problem really is Earth's atmosphere. The light gets jiggled around as it's refracted through the air on its way to you. So that's why astronomers are so fond of putting telescopes in space, as the seeing conditions are much better up there. Well, then, if you've got good quality optics and you get out of the Earth's atmosphere, you still can't read a dime on the date on a dime on the surface of Mars. Okay, the problem is diffraction. When you clean up everything else, you come up against the diffraction of the light as it enters the optical instrument. Okay, any kind of a telescope or microscope, or for that matter, the eyes in your head, the waves pass through some sort of an opening as they enter it. And when they do, they diffract, just like the light that was going between the jaws of that caliper over there just now. And just as the central maximum over there on the whiteboard was bigger, probably 2-3 times bigger than the spot you would see if I took away the slit and just shined the laser on the whiteboard. the light spreads out when it enters your eye or a telescope for the same reasons. It diffracts, okay? So here we have some sort of an opening. For the moment, we're going to consider it to be a rectangular slit like we've been talking about all along. And these dotted lines that I drew, those are the edges of the central maximum. That's a good boundary to pick for the main part of the light coming through the thing. You do have these side orders over here, these increasingly faint side orders, but the majority of the light's energy goes into the central maximum. So let's say that the image of the star is a blob of light, and the angular radius of that blob would be this angle theta from, from right straight through over to where the first minimum is. You take the equation for where the first minimum, from the previous page, the minima are at a sine theta equals m times lambda. So the first minimum, you put in m equals 1. And, well, usually optical instruments have a circular aperture. I mean, once in a while you come across something like a cat's eye. But if instead of a rectangular opening, if you've got a circular one, it's pretty much the same discussion, except it introduces a factor of 1.22, which is a little further down the page there, where we'll get to it in a moment. But it's a minor variation on the same story. So here's the two binary stars, and light from each one enters the instrument, the telescope, and creates an image on, in the old days, they used photographic film. Now it would be some sort of electronic detector. The stars are point-like sources, which is why they're such a nice example to talk about. I mean, stars are big, but they're really, really far away. I don't know if you've ever looked through a telescope, but if you do, planets will resolve into a disk. Stars are still pinpoints. You magnify them 300, 500 times, they're still pinpoints because they're so far away, even though they're very big. So you have point-like sources, but you do not have point-like images. The light spreads out because of diffraction, and you have two little blobs. The standard that's been adopted is to say that those two little blobs are barely resolved if the edge of one is at the center of the other, like I've sketched over here, okay? So the center of one would be this same angle theta that I labeled up here. That's how far the center of one would be from the center of the other. So if you have a rectangular opening, I mean, we're typically talking about extremely small angles here, just a few seconds of arc. For very small angles like that, you can make the approximation that sine theta equals theta. And so if you have a rectangular opening, then that's fuzzy. Then the angle between barely resolved sources is lambda over A, where A is the width of the slit. D for diameter if it's in a circular opening, and there's that factor of 1.22. One more example, and then we're done with this unit. And there's a little shortcut in the math that I'd like to suggest before I turn you loose on that, which is that once you get into this, you're going to be dealing with a very long, skinny isosceles triangle, like in this example here. Well, what you could do is draw a line down the middle and make it into two right triangles that way. So you could do some trigonometry, but when you've got a triangle, yeah, it's an isosceles triangle, but the base angles are 89.5 degrees. That's close enough to 90 that it introduces a very small error to assume that that's 90. And say that you can calculate this distance x by saying the tangent of 1 degree is equal to the opposite side over the adjacent side. And yes. Something I should have mentioned. Actually, it should have been printed in the notes there, a little bit of an oversight. But those equations, both of these, the one you'll be using for problem 6 is this one on the right. But this gives you the angle in radians. So you might want to write that down somewhere in large capital letters, underlined a couple times like that. And if that was the problem, you might want to pause again and try the example again. But assuming you're ready for me to go over it, here's the situation. Here we have the observer. It's supposed to look like somebody's eye. Doesn't seem like it's worth the time to draw the whole face. Over here, just a second, let me turn the page. You've got the 2 headlights. Question is, how close does the car have to be for you to be able to tell whether one of the headlights is burned out or not? So here's the light ray headed toward your eye from the one headlight. Here's the light ray headed toward your eye. Nope, I don't know why I did that. From the other headlight. These headlights are located a distance x away from you, and the question is to find x when the headlights are just barely resolved. This distance, I guess there's no reason not to make it a solid line. The headlights are 5 feet apart. So, kind of like in that little example just before this that I was talking about with the Washington Monument. It's actually an isosceles triangle, but you've got a triangle whose base is 5 feet long and whose length in this direction, when you get to the answer, turns out to be more than 3 miles. And these angles are both so close to 90 degrees, it's not really worth talking about the difference. So if you're a purist, then draw a line up the center and bisect it into 2 right triangles so you can do some right triangle trigonometry, and you will get exactly the same answer that you get by taking this shortcut. So if these 2 headlights are just barely resolved, then this angle theta is equal to 1.22 times the wavelength of the light that's being used, divided by the diameter of the opening that it passes through, which in this case is the pupil of your eye. The wavelength question says to use 500 nanometers, which is somewhere around the middle of the visible part of the spectrum. So that's a good compromise number to use if you're working with white light. The diameter, (500 nanometers). Nano means 10 to the negative 9. 2 millimeters. Milli means 10 to the negative 3. So the angle between those light rays headed into your eye is a little more than 0.0003 of a radian. Okay, so again, that comes out in radians, not degrees. Now, there is actually another shortcut you can take. And if you don't like shortcuts, then go ahead and punch it up on your calculator. But hopefully at some point in some math class, somebody mentioned to you, or if they didn't, I'm telling you now, that if theta is small, okay, and I, capital letters underlined because you never want to try and do this with an angle like 35 degrees or something like that. But this is a tiny little angle we're talking about here. And when you're pretty close to zero like that, the sine of an angle is just about the same as its tangent, and both of them are pretty much equal to the angle itself in radians. So go ahead and punch up the tangent of that angle if you don't like approximations, but when you do, this is what you're going to get. Okay, so looking at my not quite right triangle here, tangent means opposite over adjacent. The opposite side is 5 feet, the adjacent side is x, approximately equals, because yeah, it's not really a right triangle, but it's very, very close. So that filling in the 3.05 times 10 to the negative 4, because the tangent is pretty much equal to the angle itself in radians. And again, if you don't happen to think of that little shortcut, just make sure your calculator's in radian mode, punch that up, and this is what you're going to get for the tangent of the angle. Solving it for x, cross multiply both sides by x, divide both sides by the angle. So 5 divided by that comes out 1.64. In other words, a little over 16,000 feet. So at that distance, even Superman standing in a vacuum would not be able to, well, like comic strips have ever been constrained by the laws, especially Superman, not really restrained by the laws of physics and what happens there. But if it was, I don't care how good your eyes are, beyond that distance, even if you're standing in a vacuum and there's no atmospheric distortion, you can't tell if both headlights are on or if one of them's burned out. And that gets us to the end of Unit 12, which gets us to the end of the material covered on the third exam.